a private message. You encrypt the message using a key made up of ones and zeros. You send the key to Bob by a secure line, this could be email or wire, and then mail the message to Bob. Remember, it doesn't matter if anyone else reads the message, they won't be able to understand it. What's important is that no one sees the key. But an eavesdropper, Eve, has tapped into the secure line. Once she has the key, she can read the message and your secret will be publicly known. This would never happen if you'd used quantum cryptography. With quantum cryptography, the key is a stream of photons or light particles. Photons have a property called spin, which can be changed when it passes through a filter. You have 4 filters, vertical, horizontal, and 2 diagonal. We'll lump these into 2 groups, the diagonal scheme and the rectilinear scheme. To translate photon spin into a key, a photon with vertical or this diagonal spin means 1, and horizontal or this diagonal spin means 0. If you wanted to send 1100, you could send this sequence or this one. You start sending Bob photons, switching between filters at random. Now here's where the Heisenberg uncertainty principle becomes important. The only way Eve can measure a photon spin is by passing it through a filter. If Eve measures this photon with a rectilinear filter, she'll guess correctly that it has vertical spin and note down a 1. But if she uses the diagonal filter, the photon spin will be altered as it passes through. She now incorrectly reads a 0. The same will happen if she measures a diagonal photon with the rectilinear filter. Unless Eve knows beforehand which filter to use, she runs a pretty big risk of changing the spin. And because you're switching between filters at random, she'll get it wrong about half the time. The laws of quantum physics prevent her from knowing the key. Now you may have spotted a pretty big problem. Bob is in the same boat as Eve. He doesn't know which filter to use either. This problem actually took a long time to solve. After all, what's the point of a message so secure even the receiver can't read it? But there is a way around it. After you've sent the key, you call Bob and tell him which scheme you used for what photon. You don't tell him the spin of the photon or whether it was a 1 or a 0, just whether it was rectilinear or diagonal. If you used the right filter, you both keep the digit. If you chose the wrong filter, you get rid of it. Probability tells us that he got about half wrong, so you keep the half he got right, and that's your key. If Eve is listening in on your conversation, it won't help her. Say for the first photon you both used a rectilinear filter, so you keep the digit. Eve used the wrong filter and she can't tell if it's a 1 or 0 from just which scheme you used. For the second photon you used a diagonal filter, so did Eve, but Bob used the rectilinear filter, so you get rid of this answer. So now you and Bob have a totally secure key, and Eve has a bunch of useless 1s and 0s. When the first quantum cryptographic system was tried in 1989, a key was sent 36 centimeters from a computer called Alice to a computer called Bob. Now newer models have reached 150 kilometers. There's still a long way to go, and some people think this is a whole new era for privacy. Quantum cryptography is different from any encryption system before it.